So now I want to start a new section, or new chapter rather. This is going to be section 2.1, linear functions. And again, a lot of this will be review, but we're slowly pulling away from review and getting into potentially new things. So there will probably be some things in here that some of you haven't seen before. So we've got 3, 15, 23, 45, and 59 for your suggested exercises. And we've got a whole slew of definitions, and some of them you'll know, some might be new to you. So we got slope, then we've got these things like point slope form, we've got slope-intercept form, and finally, well, I guess we'll just leave it like that. Then we've got linear and constant functions. We've got parallel. Phone was on, sorry about that. Parallel, perpendicular, and average rate of change is something that you may have not seen before. I mean, we've discussed it in class, but then you've almost certainly not heard of a secant line. Okay, I could be wrong. Now I'm going to ask that you work through examples 1, 3, and 4 in the book. Okay, so we're going to do a lot of this with points P1 being, having coordinates x1 and y1, and the point P2 having the coordinates x2 and y2. So again, these are coordinates, not intervals. Okay, so these are the coordinates for points. Then we can define the slope of the line through these 2 points by, and we often call this m, just m is often used for slope, y2 minus y1 over x2 minus x1. And sometimes you hear this called the rise, because it's the change in y, over the run, because it's the change in x. So it's like the vertical change over the horizontal change. Now note, a horizontal line has a slope of 0 because we're going to have y1 and y2 the same, so the numerator is going to be 0. But a vertical line has undefined slope, or, and I don't like this term, but it's sometimes used, no slope. So it's technically correct that it has no slope, but if I have no dollars, then you would say I have $0. Not like a dollar amount of 0. But if a line has no slope, it doesn't mean that it has a slope amount of 0. It means it has no slope, not even 0. It has an undefined slope. So I prefer the nomenclature undefined, but use whatever you'd like. So let's do a quick example. Find the slope of the line through. Let's do 2 points here. Let's do 4, 5 as my first point, and we'll do 7, 3 as my second point. Okay, so I'm going to do solution. So the slope is going to be, and again I like to write down the formula, y2 minus y1 over x2 minus x1. So I'll do the difference in y values. So I do 3 minus 5 over the difference in x values, 7 minus 4. Now it actually doesn't matter which point I do first, just as long as I keep it in order. So if I do 3 minus 5, then I should do 7 minus 4, not 4 minus 7. That would throw in an extra minus sign that we don't want. Okay, 3 minus 5 is negative 2, 7 minus 4 is 3, so our answer is negative 2/3. I guess this is fine too. So the slope of the line through those 2 points is what we'd call negative 2/3. So I'm not super big on names of things, but I will give you a few names just because I might use them. I might say these things, but I don't really like to do a whole lot of testing over, do the point slope form or do the slope intercept form or whatever. There might be one or two questions, but this isn't huge to me. It's more just so you know what I'm talking about. Okay, so the point slope form is going to be, of a line through the point x1, y1 with a slope m is, and here's the equation that defines that, y minus y1 equals m times x minus x1. And if you notice, if we divide both sides by x minus x1, we just get the definition of the slope with one of the points, and then with x and y just ranging through the rest of the line, with the exception that, of course, we can't divide by 0, so we couldn't have x equals x1 for that definition of the line. Okay, similarly, slope-intercept form of a line with slope m and y-intercept b is, and this is my favorite, y equals mx plus b. This is the way that I think of lines. I think y equals mx plus b. I don't know if I missed the day where we covered that in class, but this to me is a line. Finally, we have something called the general form, which I'm not really into, and that's just ax plus by equals c. I like to call it the neural form. I'm not really into this one. Okay, it is a form, but I'm just not really into it. Okay, so each of these are all linear functions as long as the coefficients on x and y are non-zero. Okay, if like here we don't, it seems like we don't have a coefficient in front of y, but the coefficient is 1, of course. Now the constant functions are x equals c. Sorry. Write it like y equals c. So in this case, this is our f of x. Our f of x is just a constant. Okay, so two lines are, I guess, I said these are linear functions. I should say these are linear equations as I've written them. For it to be a linear function, it would have to be like this. This one would be a linear function. F of x equals, some non-zero constant times x plus some other constant that could be 0. So this just can't be 0. That's probably not really readable. Let me zoom in on that for a second. So this is a linear function. We've got a linear input. So that is we've got an input x, and we're multiplying it by something that's non-zero. Okay, so that's a linear function, I suppose. These are linear equations which can be turned into linear functions. Okay, so we say two lines are parallel. You can remember how to spell parallel because it's got two L's in the middle, just like parallel lines. If they have the same slope. Two lines are perpendicular if they have slopes m1 and m2 with, we have m1 equals -1 over m2. That's what it means for things to be perpendicular. We would also say that they meet at right angles. We haven't carefully defined this yet, but hopefully you have some idea what this means. Okay, so perpendicular lines will meet at right angles. So parallel lines, same slope, perpendicular lines meet at a right angle. Well, that was kind of a not so great. There we go. So this has to be a right angle. If you don't know what a right angle is, don't worry about it. We'll get really excruciating detail on right angles later. But basically like the corner of a square. Okay, so that's parallel and perpendicular. Let's do a quick example involving parallel and perpendicular. Find a linear function A parallel to and B perpendicular to, just really not writing well right now, perpendicular to f of x equals, let's do 3x plus 4. Okay, so solution. So A, we just need, for parallel, means we need the same slope. So any function with m equals 3. Will do. Let's set g of x equal to 3x plus 9. The 9 is not special. All right, it's just the, whatever. This is the important part, is that it has the same slope as this. So for part B now, we need our new slope to be -1 over the old slope, right? That's for perpendicular. So just anything with -1/3 in front of the x. So let's set h of x equal to -1/3 x minus 17. There we go, that'll do it. Okay, so the last thing that I want to do with this lesson is define the average rate of change. So the average rate of change of a function f of x over an interval AB is defined, and here's how we write this. We're going to write this as delta f over delta x, and this is equal to f of b minus f of a over b minus a. Okay, now this is just a new definition. Maybe you've heard me mention this, maybe you haven't, but this is what we're going to call the average rate of change, and I want to draw a quick graph for you here, just so you can kind of see what's going on. If I have a function f, and I've got these two x values, a and b, then the average rate of change is going to measure the slope of the line from this point, which has coordinates a comma f of a, and this point, which has coordinates b comma, whoopsie daisy, which has coordinates b comma f of b, and it's going to measure the slope of the line through those 2 points. Now we notice that the function is curvy in here. It's wigglier than that line, but that line approximates the function between those 2 points, and we will say that it's kind of averaging the behavior. Now, depending on how wiggly our function is, and this can be quantified, this average may be better or worse. And the idea is, as b and a get closer, that is, as the change in x gets smaller, this should more and more accurately give us sort of the quote-unquote slope of the curve of the function. Now, the line through the points a comma f of a and b comma f of b is called the secant line. And at some point I looked up why this was called this, because we're going to see secant as a trigonometric function we'll see later in the class. And I looked it up and it made sense to me once. Either it made sense to me or I was convinced that it made sense to somebody. Regardless, I don't remember why that's the specific name. Anyway, let's move on and do an example of the average rate of change, and then we'll just compute some average rates of change, and then we'll stop there. So example, let's compute the average rate of change over the interval. Let's do -1 to 1. We're going to do three functions here. We're going to do f of x equals 3x plus 2. We're going to do g of x equals 7. And we're going to do h of x equals x squared. Okay, so solution. Start with f of x. So I guess I should say what I'm doing. I want to compute the average rate of change of f of x, which is delta f over delta x, which is going to be f of b minus f of a over b minus a. So here's a, here's b. So this is f at 1 minus f at -1 over 1 minus -1. Not too bad. So we plug 1 in, we get 3 times 1 plus 2 minus 3 times a -1 plus 2 divided by 1 minus -1. Now, hopefully, there's a little bit of an echo here, and this looks a little bit like the difference quotient. Okay, this is not the same as the difference quotient exactly, but they're very closely related. So the difference quotient is the average rate of change between from the interval x to x plus h, right? So now if I just simplify this, I've got 5 plus -1, it looks like. Sorry, 5 minus a -1, so it's going to be 5 plus 1. This should have been a minus sign. Got ahead of myself. And then that's over 1 minus -1, which is, 2. So I've got 6 over 2, which is 3. Now that shouldn't surprise us, because this is the graph of a line with slope 3. Or this function has a graph which is a line of slope 3. So the average rate of change should be 3, because that's the slope of the line everywhere. So if we graph this, 3x plus 2, we're going to have this line with slope 3. So if we pick 2 points, at +1 and -1, and look at the average rate of change of that, that's the slope of that line connecting them, well, that's the slope of the original line. Okay? So now let's look at delta g over delta x. So this is going to be the average rate of change of g of x over this range. So this is going to be g of b minus g of a over b minus a. And again, this is g of -1, g of 1 minus g of -1 over 1 minus -1. Well, what is g of 1? G of 1 is 7. What is g of -1? G of -1 is also 7 over 1 minus a -1, that's 2, but this is just 0. And this should not be surprising, because if we graph g is just g of x equals 7. So if I compute the slope of the line through these 2 points, it should be 0, right? It's a horizontal line. Okay, let's now do one more final example here. And let's let h of x, h of x is x squared. Let's look at delta h over delta x. And this is the average rate of change of the function h of x, and I'll just sketch h of x really quickly here. So h of x is x squared, which is a parabola. And so a parabola, unlike the first two functions, this is a curvy function. So we're trying to approximate the average rate of change over this curvy function. So let's see what that's going to turn out to be. So again, this is going to be h of b minus h of a over b minus a. Well, h of b is going to be b squared. Sorry, it will be, but h of b is going to be h of 1 minus h of negative 1 over 1 minus negative 1. And so let's plug this in. Well, this is 1 squared minus negative 1 squared over, well, 1 minus negative 1 is 2 again. But what's this? This is 1 minus 1 over 2. This is just 0. How is this 0? Why would that be? Well, let's look back at our picture. This thing's symmetric. So if I look at the line that goes through these 2 points, the secant line here, it's a flat line. It's an even function. So there we go. The average rate of change, even though there's a whole bunch of stuff changing, the average rate of change is 0. We went down, we came right back up again. So this might be new for probably most of you, and this would be kind of the main takeaway from here. The rest of the stuff you've probably seen before. Anyway, I hope this made sense. Talk to you again later.